recording this. Hopefully everybody can hear me all right. Sorry about Monday. I had my internet wasn't working very well. So got everything going, so everything should be all posted up. We're gonna get into some new exercises coming up here. I got pretty much over the next week here, we're going to be looking at service entrances and what's required for that. You know, how we get wired up, how we figure out what we need to get wired up. I'm going to have a worksheet that's posted today, service entrance calculations, and it's 3 pages, and it pretty much goes through the whole building plans and ask you specific questions, and you have to figure out, you know, the branch circuits and what the ampacity is going to be for the whole thing, and decide what size service you need to install. So there's 4 pages altogether, and the 4th page is like instruction sets for specific questions and how to figure what, you know, how to calculate voltage drops and things like that throughout the sheet. It's lengthy, but don't get bent out of shape with it. It's kind of set up to be like in sections, so that way you can basically compute through and figure out what the overall requirements are going to be for your house. So, and that one, it's about like, I almost give you like 2 weeks to go through that exercise. It's usually like a lab exercise. So that way you can go back and forth, look at the plans, make sure you're understanding it right, you know, ask me questions, and we'll get through that. But it's an important part, I feel, because we cover all the basic chapters, and then you notice I jump in, it's like 27, 28, and 29, and that's where it deals with different service entrance, you know, requirements and calculations that we need to account for. But for today, we'll start off. I have a couple of things. So based on this, it's like, yeah, the very start of this, the good, the bad, and the ugly. And I don't think I've shown you guys this video yet. So let me show you. And this is what some homeowners can are capable
house that's for sale in Everett, and I thought I'd show you an interesting little electrical trick that they got going on. This is the garage door opener in the garage. We've actually got 2 garage door openers. There they are, 2 garage doors. You can see the cord that's kind of hanging off there. Let's follow the power cord and see where it goes. All right, so it kind of goes up into the rafters, and then down, down, down. And it's plugged into a surge protector. All right, that's pretty safe. Let's pull that surge protector and see what that's plugged in. Whoa, what's that? They appear to have spliced the surge protector into some kind of wall cord. So let's follow that and see where that goes. All right, let's go along the wall, and then up, and then out. All right, well, let's go outside and see if we can find where that goes. All right, we're on the outside now. Let's see if we can find that cord. Oh, there it is. All right, so it comes out of the wall there, comes down, and oh, lovely. It's just sort of tacked to the fence here. Fascinating. That is, wow, really. Kind of under the plant here. Then you see it comes up, and it goes into up against the main house, where it runs over. Oh, pops in through there. Let's jump in. Comes in, down. Oh, another amazing splice job to a plug, which is then plugged into one of these really puny little extension cords. Let's see where that goes. Down in through this door, okay. This is sort of the little like tacked on laundry room. You come in here and oh my gosh.
Hey.
It has been plugged in to the light socket in this room. So you get power to your garage doors, presumably, when you turn on this switch, and then the surge protector, and then the garage door. Wow. For real.
Yeah. Oh,
All right, we're at a house that's...
oh, we're not at the house anymore. Yeah, these are real deals. People actually did this. They'll connect stuff up. Homeowners are very, very creative sometimes. It's like they have just enough knowledge to be dangerous. But so now, excuse me. So the next, I guess the next week we're going to start looking at service entrances, service entrance equipment, service entrance requirements, that kind of thing. What we need to do to be basically bring power into our residence and what's required with that. So today's lecture, we kind of start off with chapter 27. It's 27 and 29. And we look at a couple of important things they call the service drop and the service point. Now the service drop, that's where the power company brings from the transformer, right? They'll have overhead conductors powered up to your service point. And then at that service point, that's where basically your house and their wiring meet together and provide you with power. It's typically at the meter. The meter is from one side, it's the power company. On the other side, it's pretty much you. So they bring it in up to that point, and they cover it up to that point. They'll, if anything happens to wiring or that kind of thing, that's what they cover. But that's the difference between a service drop and a service point. And this is a typical illustration of a mast style, where you have the 3 wires going off to the pole, and it can be connected. The mast can vary. It depends on quite a few factors actually involved with your house. It could be on the side going up. It could actually come through going up through the roof. There's a variety of ways, as long as you have the mast coming out and over. And there are requirements that they have. Hold on here. This is a typical illustration, and you have both. The first one is an underground style, where you would have the green box sitting somewhere out in your yard and then connecting through, and the other style is the mast style. Either way, it still goes back to the power company service drop, where they bring the power into you. So typical things which you would have with an overhead service, right? You would have your service raceway and the fittings, because when you're exterior, even if everything's run with Romex and whatnot throughout the house, when you go outside, especially with the mast style, you have to have a conduit. And these days it could be EMT, where it's the metal conduit style, but more and more popular is the PVC style, where you get Schedule 80 plastic pipe running up, with a plastic mast head on it and everything, and it's fully acceptable. But so that would be the service raceway, and a raceway very typically it would be a pipe of some sort. It doesn't have to be. Then you have the meter and the meter socket. You have a main service disconnect, excuse me, which would be your main service breaker, very typically. And then the service conductor between the main service has a disconnect, and then a point of attachment, where you have their service drop conductors coming in and attaching to your wiring through your house. So this would be a typical illustration where we have a 3-wire system, right? 2 lines and a neutral coming into a mast, traveling down the pipe and going to the electric meter, and from the meter going directly into your main main service panel. And that's all piped all the way throughout until you get to the actual panel. And from the panel, then it's of course going out throughout your house and then distributed that way. And that does not have to be piped usually. So if we take a look at how we're connected up through, this would be a common illustration of those pictures where you can see we'll go simple. Always remember these types here are the actual circuit breakers. So it shows where it's a jumperable line. And these lines in the beginning, that's actually the transformer that sits out on the pole. So this would be literally from the very beginning, from the power company coming in. You have the main, you have the meter right here, and then you have the main breaker in your panel. And that would be whatever your service is. So if you have a 200 amp service, you would have a 200 amp breaker. 100 amp service would be a 100 amp breaker, and so on. And that would be your main disconnect, because you kill that breaker, you kill all power to the residence. And you can see it goes out through these different ones where they have them to the branch circuits. So these would be all the individual circuit breakers throughout your panel going off to their, respective loads. So this is a typical illustration. It's, very simple. You don't get the picture with it or anything like that. So a very common one in Illinois here is the mast style. Now, there's a couple of reasons why. One, you're not required to have an underground service, although they are becoming more and more popular. You actually have to pay extra to get an underground service put in, whereas like the power company, like Ameren and ComEd and those, they will install the mast style for free. If they have to trench and do the underground service, they're actually charging you money. So a lot of times a homeowner will opt out and go with the mast style setup where it's an overhead. But more and more people are getting, where they don't want the wires overhead, getting in the way over their driveway or that kind of thing. So they elect to go with the underground service. And it is neater and prettier, but it is not a requirement here. So very, very much, very, very popular is the mast style setup, where we have a pipe going up the side of our house somehow and connecting up to the main service. And NEC does cover it, where the installation of the service entrance cable, if you wanted to see, would be Article 338, would list off and show you what is required for the service. And these are the two types, where you have the overhead service or the underground service. The end connection is still the same as far as we're concerned. I mean, you're essentially coming up to a meter going into your service panel in your house. The way it gets there, like I say, it's like whether we're going up and over or down and below. So we have a few different considerations, of course, to consider, as far as what kind of equipment we're going to need. If we go with the mast style, of course, we'll need some kind of pipe or raceway going up to a cover head here. And then basically you provide the wiring up to this point. And at this point, then the Ameren would come through and splice in and attach your full service. You don't get to do that part. And very much the same way with the underground service. The only way is really in the routing, and you'd have different equipment that would go into place for underground service. You'd have to trench through, everything would be piped, waterproof and that kind of thing. But the end result is still the same, but depending on the roof, now would be the way we attach our mast and the direction that it's coming in and whatnot. So you can see if we have a mast just sticking straight up here, that we do have some kind of support attached to it. So if you have the flat style roof with a mast going up to the roof, we would have to have some kind of a support structure put into place here. And this could be either like a cable type thing or a hard pipe. And you'll see also, depending on how high up our mast goes, we may also be required to have a brace put on this style where the roof has a pitch to it. And that depends really on the height of the mast and the pitch of the roof. It determines how much support may be required. And the reason being is that, like, you have so much pipe sticking out overhead here, You know, you don't want anybody to be able to knock into it, knock it over, or anything like that. If somebody else is doing some kind of service, a roofer or something like that, you don't want them to be able to hit it. Even during a storm with a branch or something coming through and hitting it, you don't want it to knock the pipe over. So that's the reason why we would have some kind of support involved in holding the mast in place if it has like a certain length to it. And we start to get into that actually. There's some exercises we'll do, but we actually look at the overall pitch of the roof and determine based on the height of our mast, okay, if we are required to have any support to this structure or not. So there's a couple rules we would have to follow. As you see here, if we look at the roof level, if we have not less than 3 feet in all directions from this as far as our clearance goes. And the reason being, we don't want these, because there's always some sag to the wiring, you know, the service wiring that's coming in. And you literally do not want that wiring to drag on the roof or drag on the pipe or anything like that. If there's like, depending on how this is laid out, we may have to even provide a guy support for the wiring, depending on how much sag that we do have. So we do have rules to follow with that. We have to, you know, take that into consideration. That's considered our part of the deal. Again, Ameren does not enforce the code. Their primary job is to bring their consumers or customers service. So as far as getting the final code or getting the final finished code is primarily up to you to decide that, or your inspector. But this is a very common layout where we have the mast style of 3 wires coming in, right? And one key point to think about here is, remember, ground does not happen with the utility company. They bring you 3 wires, 2 line wires and a neutral, and no ground. The ground actually, if you look at the service equipment here, there's no ground at this point. Now, when you get into the meter, there is a neutral bond that occurs in here, right? That the neutral doesn't go into the actual meter, but there is an attachment. But again, no ground until you actually get into the service cabinet. And that's where you have a physical ground attached. And these days it's an 8 foot, and you haven't lived until you've had the pleasure of driving an 8 foot copper rail into the ground with a sledgehammer. And you're only allowed about, I gotta think of what it is, but you're allowed a little bit of excess above the ground, okay? Otherwise, you're literally driving this copper rail about 8 foot into the ground. And that's always a fun thing to do. It's like in wintertime if the ground's frozen or something like that. But yeah, you're attaching the ground, and then you'll be pulling a ground wire in. So your actual grounding doesn't occur until you actually get into the service cabinet, your panel. So prior to that, it's all ungrounded conductors, you know, going back up to the transformer and whatnot. And the masts, they vary in style. It depends on which manufacturer you go with. Some have more room, you know, they do come in a few different, you know, types and varieties, of course, always on manufacturer. The meter box can be a little different and everything. I mean, the essential deal is you would buy the meter box, have it all wired up and everything. As far as the meter, the power company provides their own meter. You can't actually buy those things. But you would have it coming through and then coming into your service equipment, into your house, very typically into your panel. But yeah, usually we're hard piped all the way up to this point as far as protection. I mean, you're generally dealing with these days, very typically you're pulling in a 200 amp service or even a 100 amp service. You know, it's 100 amps is a lot of amps, and you don't want to have anything going on here. They even at this point, so when you bring this in, the main fitting connector inside of the panel is actually the only spot required to have a bushing. And this is a plastic screw-on cover. It literally fits onto the connector end, because very typically these connectors that go into the service panels are metal, or even if they're plastic, they have an edge to them, and you don't want the wiring to be riding on that edge, cutting into the installation. So they actually require at this point to have a bushing on the connector. And this is the only connector you have in the whole house that is required to have a bushing. You could put bushings on every connector if you wanted to. If you wanted to go like for the safety overkill where you have no frayed edges possibly coming into contact with wiring anywhere, but very commonly just at the main service fitting, that is where you are required to have a bushing put in. Anyway, so underground service. Now, underground's a little different. Like I say, they'll generally have a green connect box installed somewhere out on your yard somewhere, and it's run by a hard pipe up to your service connection, and the pipe would come up. And there's a few varieties and styles of that. Sometimes they'll actually have like a full-out panel style box that goes underground and connects up to the pipe. Sometimes it'll just be the straight pipe coming up into the meter. There's a few different styles. Believe it or not, when you actually go on the power company's website, they actually have, and really nicely laid out too, pictorial on how or what they require as far as an underground service is concerned, which is always a good thing. You know, always check with your local power company before continuing on, even if you're doing the mass style, because there may be some things that you hadn't considered that they already know about, and they would let you know that you might be required to have this in place. So it's always good to connect, you know, check with them before the final purchase of all your equipment, just to make sure that you have everything you're going to need for the job. But as far as the underground service, yeah, bringing it into the meter, after the meter, everything else is always the same. The underground service is just purely, you know, installing up to the underground. And at this point, again, which wiring is considered the power company's and which is yours, it would be at the main service junction, which is very typically the green box that they have installed out in the yard. So you'd be required to trench through X amount of feet underground going to this point with a hard pipe, and then they would bring in their equipment and attach everything else up after that point. And this pictorial gives a pretty common layout. Like I say, you'll have a pad mounted transformer somewhere out in your yard somewhere going underground. And so what you would be required to do is bring in this service here with the underground up to this point. So you would have to trench through and run pipe with the wiring up to this point, and then the power company picks up after that. So they provide you power up to this point, and then you bring it through, and then they put their meter in place, and then you have a full connection. But they do have specific height requirements, like how high up the meter actually has to be. You know, you can't just install it like any given place. You don't want it way up here or way down here. They do have a specific height requirement within a given enclosure on the outside of your house. So that the service personnel can come up and read the meter without having to go into your residence at all. So where do we put it? So it has to be at a readily accessible location. And this can be outside the structure. You have to be careful when going inside. So and it depends. A lot of times you'll have a main service disconnect, which is your panel, out in the garage or something. But oftentimes you'll have it down in the basement. It could be at different spots. It all depends on the convenience and the locations and where the homeowner decided they wanted it, where the contractor decided they would put it in place, that kind of thing. Just remember when you have your main service that's going up to your meter, and you don't have any, there's no protection there. There's no ground fault protection, no short circuiting. You know, you want to basically keep these runs to a minimal. They actually have a specific length you're only required. Like if you wanted to, I don't know, bring it into your house in the basement, but wanted to run it all the way across on the exterior wall, you would have to actually have to check and see that length, because there is a specific requirement for that, where you wouldn't be allowed to run it X amount of feet throughout your house, and it can't be in any bathrooms. Yes, believe it or not, there has been points where they have actually had the main service disconnect located in a bathroom, but basically the rule of thumb is you want it located at the nearest point of entrance where your service entrance conductors are going to come into the house. So if you have it on the one side, on the garage, that's usually, like I say, the most convenient area. It's where you're wide open, you have access to everything. Sometimes, though, they will pull it through and they'll run it down into the basement. But again, you would have to check and see. So here's a case where, yeah, so from the main service, so you have the meter, and it goes down into the basement. Now, from the inside of the basement, that pipe runs, and you can see down a given length, and goes into a main service disconnect. And you are allowed to do that, but again, it has to be hard piped, totally enclosed, because remember, this is ungrounded stuff, so there is nothing protecting it. If it goes, it goes. But it has to be readily accessible, closest point of entry. And sometimes you may have to check with your local electrical inspector to see, like, if you wanted to run it a little bit more, or say, well, I only need 2 more feet or something like that, then you may have to go over and see if you can, if you're allowed to run it that length. Because again, too, you also have like voltage drop considerations to take into place with this. And I mean, we can always install larger wiring, but it's always cost factors and things like that, what's allowed, what we're able to do. And this is an illustration of a very typical 200 amp service with the circuit breakers populated throughout. They are required that you be identified on the service somewhere. It could be on the breakers themselves, it could be on the door panel, on the outside of the covers, or anywhere. But as long as you have like a key that shows what breaker disconnects what. and they get interesting over time. You know, if a homeowner adds things on, you always find like some chicken scratch add-ons, you know, a little pencil in, oh yeah, this includes this too, and that kind of thing. But you are required to identify. So if you do go in and add a circuit through or something like that, you put a new breaker in, you are required to label and identify what that new circuit is and what it's disconnecting. So this is it in a nutshell. What do they require? NEC 11026 tells us that your working space around the main service panel shall be 30 inches wide and 36 inches deep. What this means is you can't have anything in that spot. Nothing. Tools, I don't care what. But you literally are not allowed to go 30 inches on the sides and 36 inches out from the front of the panel. So kind of think of like a half circle around this thing has to remain clear. So a working space must be kept clear, can't be in bathrooms, can't be above a sump pump. And if there's in the door, the panel door, if it's like flush up against another wall, you have to be able to swing it open at least 90 degrees, so you're, you know, halfway open. If you can't get that door open by 90 degrees, like if the space is too tight or something like that, then it can't go in that spot. Like if you had it real tight and there's some kind of beam or something in the way and you're only allowed to get it open like a crack or something like that, you know, 45-degree angle or something, yeah, you wouldn't be allowed to put that service panel in that spot, because you have to have this kind of clearance. And this applies to everywhere. It doesn't matter if it's in a residence, in a, you know, commercial setting like a store or something like that, industrial like a warehouse or whatnot. This rule applies to all of them. So every service panel out there has to follow these rules right here are definite. And you'll be amazed at how many times you won't see that, but but anyway. So what's our mounting height? like how high do we want this thing to be? Well, there is no definite as far as where it has to be, but it does have to be mounted so the center of the three main disconnect handle in its highest position can't be over 6'7", which, if you think about it, that's actually pretty high up off the ground, you know. I mean, I guess it depends on the situation. There might be, you know, moments where you would have the service panel located kind of high like that, but you know, commonly you don't even see them that high. But there is a rule, yeah, you can't have it over 6'7", because then it can't be reached readily without like a major ladder of some kind. But and how much headroom? So you need 6.5 feet of headroom. So you have to think about like, okay, what do I have over the top of this thing? So you have to be careful of this. There are exceptions, very rare, but if you already have like your existing house and this is where they've had the service panel before and that kind of thing, you are allowed to relocate. Like if you were putting in a new service panel, I don't know, and you'd have to think like in a basement area where you don't have a lot of head height, you know, the old style basements or something, and that would be allowed. But usually you want about 6.5 feet of headroom up and over this thing. So you literally have, just think of where your service panel is, would just be a wide open area where nothing's put in front of it. And then you go look, and usually everybody's got all their tools piled up in front of the service, and you know, the service panel and whatnot. And it's, but people don't know. Anyway, and then we're going to go into how we size the conductors. Now, usually the largest wiring you're going to have in your house is going to be from your service entrance wiring, because that's usually, you know, pulling in, especially if you have like a 200 amp service, and you have to look at how much length is going to be involved, and that's going to tell us what size wire we're going to use, right? You got to think of our voltage drop. So if it's really long, we know we got to go, you know, the next size up than what we would normally use. But yeah, this will be the largest wiring that you're going to use in your house, is going to be your service entrance conductors. So according to Article 220, they have to be a sufficient size to carry the load as calculated. So if you calculate out that you have a 200 amp service, then you have to figure out what the voltage drop is over the overall length, size your wire accordingly. And these days, the minimum service you're allowed to put in, if you're putting in like a new electrical service, you cannot go below 100. And you will still, I mean, it's not as common anymore, but you still run into, and they have the old style fuse boxes, if you will, where it's a 60 amp service in a house. Although these days, you know, it's getting less and less. I haven't seen a 60 amp service in a while. I have seen them. I have seen quite a few actually, but it's getting more and more phased out. But yeah, any new service these days, at least 100. And very commonly now, you often see 200 amp services going into a house. And it's all the toys, right? We get more and more toys. We need more and more power. You figure appliances compared now to like 50 years ago, we got a lot more stuff. We got a lot more power requirements, you know, dishwashers and things like that. We add more and more toys. We go to the supersized washer and dryers. Now we're burning up more amps, right? Everything's getting bigger and bigger, smarter, more power. So 200 amp service is becoming more and more the common thing, but it's not an end deal. You at least have to have 100 amps. So yeah, all utility things have requirements for the size and the guying. Okay, and guying is, right, the supporting of mass services. So always check with your local, you know, like I say, your local Ameren, Commonwealth Edison, or whoever your local utility company providing you power with. These days they often have the webs. You can go right on a website. You don't even actually have to talk to anybody. You can go right on our website and just look and see. It's like, okay, I got this house with this pitch roof and this kind of thing. I'm putting in this. What do I need here? And they'll have it listed out that you have to have this with this, and what kind of equipment you're going to be required to have for your installation. So They'll determine when, where, and how the connection will be made, right? So they'll give you a cut-in date. Yeah, we'll be out this day, as long as you got everything installed up to that point. So, and these days, most of them prefer that the service be mounted on the side of the house rather than the rear. But there's always situations, and you can check with them and see if you did have a requirement where you had to mount it in the rear of the house, you could check and see if it's allowed by them or not. But yeah, and the meter base is always a supply. That's not brought out by the power company. They provide the meter, you provide the meter base. So you wire up to that. But you wouldn't have any power until the utility company came out and actually spliced in and actually installed that meter. So with that being said, we take a little look at the cost of using electrical energy. Right. So the way they measure it out, it's by the watt hour. So you have watt hour meters. That's where you're watching these little dials spin around, see how much power we're consuming over time. Usually your billing is done monthly, as we all know, right? So, and how do they measure it? They usually measure it up into kilowatts, because that's how much power you're going to use over time. And they have a formula for it and everything, right? Let's take a look at it. See, if you wanted to see, okay, how much is this costing you, you take your watts times your hours used times the cost per the kilowatt hour and divide that by 1,000, and that's how much you're paying. You can even actually check and make sure you're not being, overbilled or underbilled. Of course, if you're being underbilled, are you going to report it? But anyway, so a good example. So let's say we look at a central AC unit, right? It runs on average about 50% of the time during like a 24-hour period on a hot summer day. So if we look at the nameplate on the AC unit, we see it's a 240 single phase 23 amp. So the local power company's charging us 9 cents a kilowatt hour. So we go through, we measure how much this thing runs. So a 24-hour period, it runs half the time, so times 0.5, that means it runs 12 hours. So then we convert the nameplate data into something we can use, right? Okay, how much is the watts? Well, watts is equal to voltage times current. Okay, so if we times, on the main nameplate, we go 240 times the 23 gives us this thing's 5,520 watts. So now we can figure out how much we're going to pay for this thing per day. So if we go with the watts, which is the 5520, hours used is 12, and 9 cents a kilowatt hour, and divide that up by 1,000, and we end up with pretty close to $6 a day for your air conditioner to run. Probably gone up since I've last done this, but but that's how you go through it. Just as part of the chapter, so we take a look at it. Then we get into a little something. Some people have a hard time with this one, but what is grounding and what is bonding? So we could say that every electrical system in your house is a grounded system. So when we say what's grounding, that means it's connected to ground or to some kind of conductive body that extends the ground. All right, and where is ground at? It's literally that. It's the earth. Ground is the earth. So when we say we're grounded, that means we're protected somehow. So when you look at something like a ship or a car or something like that where they're floating, they don't have a real ground, right? Like in a car, they use the actual metal chassis of the car as a ground. I mean, and so what it would do is diffuse the electricity out. Same with like a ship. A ship uses the metal body to diffuse electricity out because it's not actually attached to earth. But you would need something large, and what you would have to have is something really big that can absorb electricity safely. So let's say something happened in your house and you don't want the power to be going out. So let's say your vacuum cleaner malfunctions somehow and the motor's starting to burn up. You don't want the electric start shooting up, because what will happen is your motor on that vacuum cleaner would literally probably burst into flames, And since you would have no ground, it would keep feeding the electricity like that. But with a ground bond, what it'll do is it'll diffuse that electricity down and out to earth safely. And by that, it would cause the breaker to trip by the current and everything else involved. But grounding is literally a protection to keep devices from getting overpowered. And when we look at bonding, bonding isn't grounding per se, but what bonding is keeping something moving along, because current's got to have a place to go. And if we don't have a bond somewhere along different lines, we will not have current going along those paths. So when we bond something together, splicing it in, attaching 2 or 3, 4, 5, 6 wires together, so that way they all share the same current and that kind of thing. But it has to have somewhere to go. If we don't make a full loop, we're not bonded properly, then we don't have current going anywhere. And if current's not going anywhere, then nothing's happening. And we literally have no power. But the book goes through and talks about our grounding and bonding equipment. And typically in our service panel, you'll see these little guys, they'll run along and it'll be, it's like a large metal bar with a bunch of holes drilled in the side with a bunch of screws on it. And it's literally tapped into the metal shell of your service equipment. And what this does is it gives you a ground point. So if I bring my main ground wire up to this point, okay, that means now this metal bar is grounded out. And anything I attach to it after that point will be grounded as well. So this illustration goes through and shows you that we could have this ground running all over the place. And as long as we make the proper attachments here, and that's even including, jumping wires and things like that, going over hurdles. But there's a variety of different ways to bond things together. And believe it or not, the devices are already made to go ahead and attach them to, like having these bus bars like this, or even these pipe clamps where you would have the wire attached down and providing ground over disconnect services like this. So you could ground from one point to the next. But providing our ground is by bonding everything together. So your ground wire through your house should literally be all connected all together. So if I went through and tried to ohm out, like at one point of the house to another point of the house at the ground wire, I should have a really low resistance reading because they should be all bonded. Now, if you don't, then that means your ground's jumped somewhere and you have a disconnected ground, which is not what you want. So you have to make sure, and you go through and make sure everything as far as your ground is concerned is all bonded together, no matter how it has to run. And it could be the bare wire it runs through, copper wire, and it all goes back to your main ground point, which is very typically these days is that copper rail pounded down into your ground somewhere outside your house, very near to your service panel. But that ground wire will come into your house, and that's how you provide it through. And back when they used to use like your main water connect, I think like prior to 75, they were allowed to do that. So in some old installations, you may go through and find that the ground bond is literally on the main water pipe coming in. But they got away with doing that because they found that that the metal actually starts to change the metal of the pipe with the water. There's like an electrolysis that occurs with that. So it actually degrades the pipe over time. So if you do have one of those old styles where it's connected up to the water pipe, you might want to consider changing it out just to save yourself some headaches down the road. But anyway, but yeah, we have a variety of ways that we can ground things. If we have points where we go into equipment and the equipment terminates that ground bond, they have clamps where we can jump over the equipment, so we have a ground on both sides and it keeps the ground running, that kind of thing. In this case, we have the water pipe here is grounded, but if the meter's in the way, if I have grounded on this side, it wouldn't be grounded on this side. So we literally have a little clamp that fits on the pipe, and you would just literally have a bare piece of wire bonded on one side and bonded on the other. that would go through and ground out that pipe for you, if you will. And notice they have a one main wire feeding back to the service panel, and that way this whole thing is grounded and bonded and brought to the outside service. I covered this a little bit in depth just because it seems like sometimes people have a hard time with this one for some reason, and I'm not entirely certain why, but you see these ground buses, and these days they're pretty much in all service panels. And as long as you make a hard connection to these bus bars, you know, where you have different wires coming in, but always remember you have to have a main feed going to that ground bus bar. So a lot of times what you'll have is like your outside wire will come through, and it'll come through the wall or whatnot, or up through the floor, and then and attached to this bus bar. And then from that bus bar out from your service panel, that's the way you're able to run out throughout pretty much all the points of your house and bring all your bonds back together. So that way you share the one common ground. And it's very typical. I mean, whether you have an underground service or a mass style, you know, your ground's still going to come through the same way, where you have the ground rods attached outside and then coming up through your service panel on the inside, wherever that is. So in these cases, they have it all grounded out. You got your water pipes are protected. You know, you have these grounded and attached back through. And here's an illustration of a pipe clamp, and the middle one is where you would actually attach your wire to. So this would clamp onto a copper pipe, and then if you provided a copper wire to that, then that whole copper pipe would then be a grounded point. And I show different styles and different ways you could bring this through. If you had concrete poured, you know, it could come up and through. Concrete counts as a ground as well, but you still would have to have so much concrete for it to be considered a full ground. Basically, you have to have a point where it diffuses electricity coming back. That way the electricity doesn't go to the point you're trying to protect. So in this case, you have like the water pipe, and they even have a jumping bond going over to the gas pipe, if you will, insulating joints on the gas pipe. So you kind of protect your service stuff inside of the house. So that way, if you were to touch the two together or something like that, you wouldn't get electrocuted from, you know, touching two conducting pipes, if you will, if one was energized for whatever reason. Remember, piping very commonly runs pretty much where all your service stuff does as well. So it's very common to have pipes running where there's going to be wiring. So of course, if that in case, you're always going to have a possibility that something could short and something could activate that pipe. And this isn't safe to do on a water pipe. It's really not safe to do on a gas pipe. So you would have a bonding jumper installed with that clamp, like I said, and just have it jumped over so that way the entire pipe. So if something were to happen, you got a zap onto one pipe, it would still be grounded out and nobody gets hurt. And I have rules where you connect this to. We can look at NEC 250-24A, where it states that the grounding electrode conductor shall be connected to the grounded service conductor. And that's done through the panel. That's where you bring all that together. The neutral conductors and the equipment grounding conductors are often connected to the same terminal in the service equipment. They're only separated by the sub-panels within the panel. So many residential panel boards have green hexagon screws. So usually green is your utility boxes, junction boxes oftentimes will have a green screw installed on them. Receptacles, even light switches these days will have like a green screw on them, and that would be where you would put your ground onto. So anytime you see the green screw, that's your green ground bond point. So usually it's a green hexagon screw, so you could use a nut driver on it. You want a very secure fastening, keep that bond going. And then you have the ground rods on the outside. Notice that it can't be less than 8 feet. This thing is literally an 8-foot copper rod that you literally have to pound into the ground. But it should be at the very minimal 8 feet. Very typically, you don't go over that because the copper is not cheap. So this copper rod is going to be a little on the pricier side. But it has to be into the dirt, you know, going into ground. If you're like in gravel, you might have to reconsider where this thing's going. It has to be pounded into earth. That way you have a, you know, a secure grounding point. And so with that one, you know, here's your key terms to take away out of this is what ground is, what a grounded conductor is, what a grounding conductor is, ground fault current path, grounding of electrical systems, and grounding electrode. So your grounding electrode is your copper rail that you've installed outside, right? Ground is your earth bond. A grounded conductor is a conductor that's protected by ground, which means pretty much everything after your service panel. So before that, of course, is ungrounded connectors coming from the power company. And then your ground fault current path, that's something to consider when you deal with ground fault protection, when you have things installed near water and that kind of thing. So these would be takeaways from this chapter, like really understand what they mean by ground and how we establish the ground. Because normally, I mean, electricity doesn't work with the ground. The ground is attached to the device, so that the device were to malfunction somehow, that it has somewhere for the excess power to go. Because if the excess power has nowhere to go, it's going to go out of the device somehow. It could be an explosion, could be an explosion with fire, it could just be fire, but that excess energy's got to have somewhere to go in the case of a malfunction. And that's why we usually provide ground. Ground is somewhere to diffuse, to take away excess energy, so that way the device doesn't explode or anything harmful. And the key terms for bonding, you know, understand what bonded and bonding are. And literally that's just it's bonding is just that connection where I bring from here to here. So as long as they're connected like that, they're always bonded, and that way we share the path. If it's not sharing a path, then they're not bonded. So these would be key terms to take away out of the chapter as well. Some of the clamps that they use, depending. So we could have, if we have a PVC style, right, this would be the plastic, but you got the little copper rail connect up to it so you can attach to it. This lock nut has a ground screw built into it. The C clamp has a ground screw built into it. So that way you, on your connections, when you have to jump from one point to another, you would have a bond point to connect through. And that's what these would be. So if it goes up to like a service device, if somehow that's not going to allow the ground to pass through the pipe or something like that, on the one side you would have one of these, and on the other side you would have one of these, and just jump your ground wire from one to the other. And then we look at chapter 29. I know this is so much fun. You guys just want to keep this going, but this won't be very long. But this gets us into that worksheet that we're going to be looking at, which I call the service entrance calculations. And this literally is going to be looking at the prints for the house. You're literally going to take apart the house piece by piece, right? Appliance room, the kitchen, the bathrooms, all my service branches, you know, my lighting branches, and figure out overall how much power requirement I'm going to need for this house. And so I give you like close to 2 weeks to do it. That way we can go back and forth with questions and stuff. But it's 4 pages altogether on Blackboard. 3 pages are all calculations, and the 4th page, everybody always overlooks it for some reason, are instruction sets for the questions on, you know, what calculations you might have to use, or, you know, what things you're going to add in where and that kind of thing. So we're going to start looking at that. Service entrances, okay? So, and like we stated before, you know, all single family dwellings these days, NEC requires at least at the very minimum 100 amp service, right? If you're going to have electrical heating system, which is not real popular, but they are out there, or where you're going to have future expansion, you know, you want a nice good sized panel, then you're looking at a 150 to 200 amp service. And in fact, commonly these days, a lot of new homes put through are 200 amp services. I mean, you may not need it now, but you know, 20 years down the road, you don't know, you might decide to go ahead and put in that pool or something. But in any case, but yeah, very minimum 100, but 150 and 200 is not unheard of these days. But to be sure that we're getting the right thing for our house, we have to be, you know, we don't want to go under. Like if our house is going to require a 150 and we put in a 100 service, yeah, there's going to be disappointment going on here, because certain things are not going to be able to work. We're just not going to be able to populate. So we literally wouldn't be able to put in the amount of circuit breakers for all the branches that we're going to need. So we would have to think about that. And that's why we go through and do service entrance calculations. So most places, they'll have like a worksheet based on, you know, you'd get like, let's say the contractor gets a set of plans in that he wants to make a job bid for. He would have like a worksheet very similar to like this, with probably a company logo on it or something like that. And you would go through and very, very, like we've been doing little by little, right? So what's the square footage of your house? You know, and then we know you have to do your 3VA, right? We get our lighting branch circuits done throughout this thing. So this is kind of how we start off. It's like, okay, what are we going to need here? So remember, VA is apparent power, you know, power, my ability to deliver that much power. And some new terms that we get into, you'll see a lot, in fact, a lot of stuff where it's called RMS. And it's a special term, and it's root mean square. And what that means is how much voltage I'm actually allowed to use. So if you were to look through and see, you know, an AC wave is like a sine wave. It's always moving and always changing. Now they have a thing in there where they call it, you know, how much voltage peak that it has. But on that peak is not true power or true, you can't utilize the 100% of this electricity. So what they did was, there's a calculation that you go through, and it's called root mean square voltage and root mean square current. And that is the full amount of power that we're able to use. So a lot of times you'll see, even on meters these days, where it says true RMS readings available. And what that means is this is true power that we're able to use. So what the NEC does tell us in 230.42 is that the service entrance conductors, right, that's basically the lines coming in from the transformer, have to be sufficient to carry the load as calculated. So you have to be able to deliver the power required, right? So we have two methods we can do. There's a conventional one that's in Article 220, Part 3, and there's an optional one that's in Article 220, Part 4. Now, in certain parts of the country, and this really applies to like in the Southwest or Florida or something like that, where you have like real hot temperatures going on. So you have to take special considerations into what kind of insulation we're going to be using with our wiring, because they're very typically going to be about like 30 degrees higher than what we normally operate at. So when you have special considerations like that in your region, you do go to different charts and different tables and pull that off. You know, always match this up to the zone you're working in. What are your temperature tables that you have to deal with? So they do have correction factors, and it would have like temperature correction factors. So let's say you're normally used to using this, let's say I use number 4 for this all the time, but now I'm in New Mexico, so number 4 isn't going to cut it. So what are our correction factors? Well, if you looked up in table 310.15, section B, subset 2, subset A, you would find the correction factor table for the different conductor sizes. So going through the worksheet, you'll go through and I have you go through, like I say, what's the square footage of your house, multiply that out. And then on these each individual lines, okay, so see how it's minimum number of lighting branch circuits, your small appliance loads, right? So you have to go through and decide, well, for small appliance loads, there's a minimum of two 20 amp branch circuits in there. And that's just required. You may need 3, you might need 4. It all depends on your house. But if it's 2, it's 2. Then you got the laundry area to consider and whatnot. So you'll go through and each one, okay, and this can all come out of the textbook and this chapter and stuff, where you're going to be able to see that. And like I say, on a very page 4 has instruction sets on what calculations you might have to do and whatnot. But you're going to go through the service entrance calculations and literally spell these out line by line. And this is based on the plans, right? So, you know, how much VA is the water heater going to need? How much is the dishwasher, the garage door, any water pumps, microwaves, if you have a trash compactor, da 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 da. So this table has where you can pretty much add in all appliance loads as well. So we're going to figure out what our appliance loads are, what our lighting branches will be, you know, what our square footage is. We're going to have demand factors, and this comes in, and this is the part where it actually is like for, especially for the HVAC guys and stuff, this is the part where you would really be looking at, because this is where you're dealing with the furnaces and the ACs, which are usually the biggest power requirements you have in a house, right? Those are your AC and furnace usually are your biggest power draws, specifically the AC unit. But that's a special note for you guys. And like I say, it'll go through and you'll determine based on the plans, what the plans require, and literally fill this sheet out until you get to the very end. And then, and that's pretty much it. But we get to the very end and we figure out, okay, based on your findings, what is your minimum service going to be required for this house? Are we going to go with a 100? Are we going to go with a 150? Are we going to go with a 200? And why? And so you're literally going to go through and based on your plans, fill all this data in, and then you're going to tell me what size service you're going to put into this place. And we always have fun little pictures. People get creative. Yeah, remember that rule where I said you have to be able to open the panel up so far? Well, you also have to be able to close the panel. At no point should you not be able to shut your panel. But, and this is creative, right? The problem being is there literally is no mast here. I mean, you're connected through, you got and that's a guy wire, by the way, where you'd have a cable clamp of some kind supporting it. But if it's grandfathered in, it's allowed. If it's right, I don't know about all that. But, and this is actually a very good illustration of what it typically should look like. Notice everything is always bent and pushed out of the way of the actual circuit breakers. You want to keep it neat and clean all the way throughout. Generally, what you do, if you notice, the space on the sides of the panel is where you run the wire. So I bring my wire and see nice and neat loops up and over. Give yourself enough slack where it's out of the way, because you don't want all the wires bunched up in the panel. You want to be able to have access to stuff. Because if I want to go through and put in a new circuit breaker, I don't want to have to fight all this wiring that somebody has in my way, right? If all the wiring's routed on the sides and looped around, depending on where you're coming in, that's totally what you want. So if you have to bring in wires in this way, route it down on the bottom and bring it up and then over and through, but keep it nice and neat and out of the way. That's the way you want to always do service panels. See, the one on the left, that's what you want. See how it's nice, even bent at angles to keep the wiring nice and clear. So if you had to go through and troubleshoot or something, you have good access. You could tell what wire is what. The one on the right, I would walk out. I would walk off of this job and be like, you're nuts. There's no way in hell I'm going to do
They
that.
had a fucking fire.
Oh, yeah. I mean, you know, it's a total fire because why? Because he got crazy.
Oh, they had a fire. Look at all the burnt wood.
Yeah. And then the fun part is now you're gonna have to go from, how do you redo it? Well, you do. You redo the whole thing, and that's why you keep everything out, keep the insulation down, don't have exposed wires, keep everything nice and neat and pretty, grounded, bonded correctly. You don't have to worry about anything. It's a nice, neat job. It doesn't take that long to do this, believe it or not. And I know a lot of people, they get down to the end of the job, you just want to finish and get in and get out, but you want to keep this pretty. And I always say, if it doesn't look pretty, then you haven't done a good job. You want to be able to stand back and look at that panel and go, is that pretty? And if it is, then you did a good job. If you look at the thing and it's something like, it's like, what in the hell is that? Then yeah, that's not going to be good. So what's wrong with this mast, if you will?
PVC.
Well, he sort of has the guy. See, there's no real support. So what you have to have would be guy wires or even a pipe structure. Like if it was a pipe hard tapped onto the house here to support it. Because if you came along and swung on this pipe, you're probably going to be able to pull it down and out of the way and bend it or something, right? Which is what you want to avoid. So you'd have to have some kind of supports involved to keep this mast from being able to be pulled in any which way. And that's really the way to look at the mast. If there's any way that you have enough pipe up where somebody can grab it and yank it, and why would anybody do that? I don't know. But think of it that way. If you can grab it and yank it and pull it and bend it or something, then it's going to need a support of some kind. And that's kind of a rule that you would want to, yeah, this one's creative. He used a bucket, and notice it's like his service drop thing. So he literally has all his receptacles mounted in the bucket and then just hooks up to it. I thought that was creative. And then again, and like even when we go through and look at like what boxes can handle, you got to think about that. Is there any way in hell that this little gem box here is going to support all this wiring? No, absolutely not, right? No, and more no. And again, and then, yeah, and real nice, pretty bathroom remodel and everything. And there's your panel. Literally in the shower, right? Look at this crap. Right over the tub. Yeah, what could go wrong? And even just for fun, we got a receptacle right there too. That way, in case you want to blow dry your hair while you're taking a shower, I guess, right? But and it's you just have to. You really have to wonder about people. And these are installed in bathrooms. And even if you get creative and pretty and try to do it up and everything like that, it's like, okay, wait a minute. You're going to take a shower in there? Uh-huh. Now remember, at the very minimum, these are 100 amp services that are installed in this thing. And you wonder why they have the code. And it's like, yep, you can't possibly protect people. Well, really, the biggest problem is homeowners doing their own work themselves and thinking they know what they're doing. But yeah, in this case, fail. Yeah, rule of thumb, never, ever install service entrance into a bathroom. Just never, ever. Because it's just not allowed. So yeah. And then like I say, support. Whenever you have to deal with a mast, think of support. So if you have the minimum where it's just rising a little bit above the pitch of the roof, and you don't have any way to possibly swing the pipe or anything like that, it's secured all the way down the wall of the garage or whatnot, then you're pretty well covered. But like I say, if you have X amount and it goes up and above, and, you have to look at the pitch of the roof and how much height you have involved. And that's part of the chapter in 27, but that's really what they're talking about. It's like being able to pull it or bend it. And so whenever you have a flat roof, it's almost a given that you have a mass style on there, you got to have a support. Either a hard pipe, hard piece of metal attached through somehow, or what they call a guy wire, where you have like a steel cable attached and fastened through real tightly. But yes, you always want these things attached, secured and fastened. But yeah, 27 goes through and talks about that and the grounding and bonding. So if you guys have any questions with that, let me know, because sometimes I know it's new concepts. But and then in chapter 29, it goes over to service entrance calculations, and that's really the big takeaway from that is I have posted now your service entrance calculation sheet, and I think I gave it's not quite 2 weeks, but about 2 weeks to do, because it's 3 pages of calculations. But I want you guys to look at the prints and go through them and calculate through based on the square footage of your house, what power requirements you're going to have for your appliances and your branches, and figure all of it out, and then tell me what size, based on your findings, what size service you need to install in this house. But that should be all your homework coming up. And then I think we're going to have a chapter 3 and 4 quiz as well. Stop that. And then, yeah, and I am sorry for Monday, but hopefully we don't have that happen again. But everything should be posted and graded and whatnot as of today. And if you look at the course calendar, you should be able to see all of our upcoming due dates here, right? I think I got everything listed now. Yeah, and there's another article we're going to have, which I call the basics of overcurrent protection. So it's an article on basically like, well, you'll read it and you'll let me know. No. But yeah, I had a worksheet for voltage drop exercise to do. And the way that one works is you literally have to figure out how much voltage is lost over a given amount of footage, and then decide, if that's just to get you used to deciding if the wire size you use is going to be good enough for that run or not. And then we'll look at the chapter 3 and 4 quiz will be due by Sunday. And then the article on chapter 28 homework will be due next Monday. And then, like I say, the service entrance one, like I don't have that due till July 1st. So, but start working on that, because there is a lot to go through. And like I say, look at page 4. It's got like most of the special instructions. And if it still doesn't make sense, get a hold of me and we'll cover it, whatever you need or you're struggling with or something like that. And we'll go over it, because I don't think it's not that bad. Once everybody gets into it, usually most everybody does pretty well with this one. It's kind of a fun exercise, but being able to sit through and actually calculate out and see what your house is going to require, kind of a fun one. But that's pretty much everything I have for today. Like I say, you get through those couple of exercises. I got a couple of worksheets with the minimum lighting thing, and then the chapter 27 homework, and then the chapter 28 homework. Your chapter 29 homework per se really is that service entrance calculation sheet, is really the nuts, the nuts and bolts out of that chapter. So that would be kind of your chapter 29 homework, if you will. But I would start working on that worksheet, and then yeah, do the article and do the chapter 27 and 28 homework as well. And that should get us through the jump chapters. And then after that, we'll jump back and start up with chapter 5 and continue on from that point and start looking at more of the basics required. We'll start getting into some of the special kind of protections, overcurrent protections like GFIs, and then we'll take a look at AFCIs after that, and some special considerations to our house. Even to the point of doorbells, we even look at doorbells and little transformers. So we'll get through pretty much most of the basics through installing, the wiring for our house. Okay. Any questions? Or did I put you guys to sleep? Everybody's passed out. Was that a good? A good afternoon snoozer.
I could go for a nap, but I didn't take one yet.
Well, and that's why that's why you should have the textbook. So you really want a good one, you just open it up and start reading, a good chapter. I always say a good way a nighttime read for going to sleep is get a good technical manual and just start reading. And if you make it through a whole chapter, then you must not be very tired. But
Got a Caterpillar technical guide that I got to go through and do a test on by the end of tomorrow. So I got some good sleeping reading.
well, there you go. Yeah, see, that was always my favorite one. It's like, well, you guys need to study this. And it's like, this is 50 pages of dry technical stuff. Are you serious? I could do maybe like 5 pages at a pop, but yeah. Well, yeah, even the book is kind of like that. That's why usually it's like the only way I can make you guys read the book is basically doing the homeworks where you have to look for the answers. But no, I never did like technical manuals. Get a good Alan Bradley VFD manual. That's always a fun read.
Yeah, but if you don't want to do nothing for the day, it's a good way to get away with about 5 or 6 hours of the day.
Oh yeah,
Not have to do nothing.
Training, yeah. What did you do today? All training hours. Training. It means you milked it. No, I know. I've done that. Well, the good thing, though, I mean, well, it depends, but have you gotten into any of those training classes, though, where they actually have you go through and do like some of the setups and the PLC setups and stuff? Because those can actually be kind of fun.
I've done some setups on like robotics with Fanuc and Motoman. I've done some of them classes for the week.
Like simulation?
It's like a 40-hour class. Yeah.
Mm-hmm. Yeah, the Fanucs can be fun. Motoman's kind of fun, too.
And so you got to call them and actually ask them for some technical advice, and you can't understand them because they're from Italy or somewhere else.
Yeah. Oh, Motoman? Yeah. Because who's Fanucs? Aren't they? They're Asian, aren't they? Or no?
No, Motoman's Asian. Fanuc's Italian.
Oh, that's what it was. Okay, yeah. And a horrible thing with that too is Fanuc's one of the more popular ones out there too.
Yep.
But they use don't they use like mostly like Siemens servo motors on theirs, I think? I'm trying to remember now. It's been a while.
They're going with Toshiba now.
Oh, they went with Toshiba.
Or at least that's what they use at the tech center.
Okay. That's an interesting one. Of course, servo motors these days compared to what they used to be are something else. Fully programmable.
Yep.
You got to be careful. Believe it or not, you can get a virus for those. Did you see that when that Iran nuclear facility started having all that trouble? This was like years back. Oh, yeah. So, yeah, their Iranian, one of their nuclear enrichment facilities started experiencing all these crazy technical problems with all their Siemens-based units, right? So they're all Siemens programmables. And somehow they had gotten a virus that only attacked Siemens protocols. So all their servo motors were turning off and stuff like that when they weren't supposed to, and other fun little things. But they never could figure out how they got that virus. No. But yeah, that's all.
But
That's all the fun.
They probably called it the company.
Yeah. And to do tech support and figure out how they got that virus. I think that shut their nuclear thing down for over a month. Yeah, they literally.
And the tech support's probably the one who gave it to them, so they had to call them in to make more money.
That could very possibly be too. I didn't even think of that angle. But yeah, that's the route they're going now. I mean, even your house to this point in this day and age, and people don't think about it, but you start networking your house up, right, and getting everything going. What happens if somehow your network gets a virus in it, starts turning your appliances on and off whenever it wants and stuff like that? It's like, I don't know. Automation, gotta love it.
Eh, Yep.
But anyway, I'm sorry. Sidetrack, but yeah, do you guys have any questions on that? Does it seem
Alrighty. Well, you guys have a good weekend, and I'll see y'all on Monday.
all right? All right. I will see all you guys. Yeah, and definitely Monday. Well, I better be on Monday. Oh,
Tom,
yes.
I know you said we have a couple weeks for the service and feeder worksheet.
Yes.
If we wanted to start on that, how do you suggest doing that? Is there any specific place in the book that would help us?
Oh, really? It comes out of like chapter 29. It goes over all the points on that, and then, like I say, at the very out of that, there's 4 pages in that worksheet. The very fourth page is like all like any special instructions and that kind of thing.
Right.
So look over that page, and then yeah, definitely look through chapter 29 because they kind of point you to the way, like where you're gonna find these if you can't find like the calculation or the formula or something like that. It'll point you where it's at, and then that way you can go through it. Otherwise, everything's gonna come right out of the plans as far as like square footage and even all the appliance ratings. So kind of look over the plans and get where your numbers are at and start pulling those in. And then, like I say, get your square foot. The biggest one, the hardest one, just for you guys, honestly, is getting the correct, and we'll go over that, but getting the correct square footage of your house. I do have that number, and I've had several numbers given out to me in the past. Some of them are correct and some of them are not. So basically the hardest one that you're going to have right off the get-go is getting the correct, because everything's going to be based on that, right? Having the correct square footage. So make sure you start looking over and getting the correct square footage, and then pretty much we'll work from there. But if you go get this correct square footage and even email it to me or something like that, and then I'll let you know if you have the correct answer or not. And I grade these really lightly. So let's just say if you did, for whatever reason, because you're going to make me do some work then, but if you did go through and get the incorrect square footage and your stuff is based on that, I'll mark you off on the square footage part, but I won't kill the rest of your answers as long as they're done correctly. You know what I'm saying?
Yeah.
So if you do get that wrong and everything else is correct, that would be the only points you would get, against you. But yeah, try getting from the beginning, try getting the actual, and based on the rules we've learned so far, right? What we're allowed to use for square footage, right? Not the garage and that kind of thing. So get the correct square footage, and then from that point, we kind of work our way forward, and then we'll start pulling the plans apart and getting like all the information. Everything we need is on those prints. So
Okay.
this kind of just, like I say, it goes step by step, but yeah, get the square footage first. That's the, believe it or not, that might be one of the hardest parts of the whole thing, is getting the
All right.
actual correct square footage, and then based on that, then everything else kind of starts to flow together. But yeah, chapter 29 is where they pretty much go over, and basically this almost comes out of chapter 29 pretty much, but they'll have examples and stuff like that too. All right.
All right. Sounds good. Then I was going to also ask about when you were going to open up the chapter 3 and 4 quiz, because I seen that it has a password on it.
Oh shit. Good point. Good point. Hold on here. Yeah, because I made that. We will. Hold on we'll make it available now. Otherwise, it can't be a take-home quiz. All right. I'll post it on the announcements too, but I'll give you the password. Here is outlets. OUTLETS, all lowercase, outlets.
Gotcha.
But I'll post it on Blackboard as well. Yeah, back. Excellent point. Thank you. Yeah,
Awesome.
I would.
Thank you.
You're welcome. You're welcome. I will see you guys on Monday.
Yep. Enjoy your weekend.
You too. Yes, that would be that.